the dimension in energy of the fermion field is 3s. Then there is another multiplet which is used to describe the massless particles, which is used to describe the massless vector particles. So this is the multiplet that is used to describe gauge bosons. Gauge bosons, if you don't break the gauge symmetry, are massless vector, are massless spin that elicit one particles. So they are described by this multiplet of particles, and in terms of field, they are described by a vector field, which describes indeed the spin one particle, and a fermion field, again a left-handed fermion field. There is actually a third case. If you want to describe a massive multiplet of particles that contains a spin one particle, you have to use what is called a massive vector multiplet, which is a more complicated object. However, we will only consider these two field multiplets. So the summary is, if you have a supersymmetric field theory, all the fields must belong either to a scalar multiplet which contains both a scalar field and a fermion field, or they must belong to a vector multiplet which contains a vector field and a fermion field. Okay? And now, I come to the rules to build the most generic supersymmetric field to each generator of the gauge group. In the case of U1, you only have one generator, so you only have one gauge field, the photon. If you have SU3, like in the case of QCD, you have 8 symmetry generators, so you have 8 gauge bosons, the gluons. In general, you associate a vector field to every symmetry generator. And then on top of that, you also have the freedom to add to your Lagrangian any gauge invariant non-derivative function of the matter fields, and that is the most general Lagrangian that you can write. So, how do you write the most general supersymmetric gauge Lagrangian? So again, first of all, you have to specify the gauge group G. Then, since the fields are organized in multiplets, in supersymmetric multiplets, you have to specify what are the scalar multiplets of your theory, and what are the quantum numbers of these scalar multiplets under the gauge group. And then you have to associate to have, as before, you have to associate to every generator of the gauge group a vector field, but the vector fields in supersymmetry are always accompanied by a fermion field. So you have to associate to each gauge generator a vector superfield. And then here you have the freedom to add to your Lagrangian a generic non-derivative function of the matter fields. In this case, you have the freedom to specify what is called the superpotential, which is a holomorphic function of the scalar fields of the theory. And if you want the theory to be renormalizable, this holomorphic function must be a polynomial of degree at most 3 in the fields. Okay, so this is a bit abstract, and the next time we will see how this translates in practice in the construction of the MSSM. So what I want you to remember that to specify a supersymmetric gauge theory, to specify the gauge group, the chiral superfields, and then the vector superfields are determined by the gauge group. And you have this function also, which you have to specify, which is the superpotential, which is a gauge invariant polynomial in the scalar fields. Once you have specified all these things, you have this rule to write the supersymmetric Lagrangian. The point is that you want the Lagrangian to be invariant under supersymmetric transformations, And this is the only Lagrangian which is invariant under supersymmetry transformations and gauge transformations. So it has this structure. So you see there are 4 types of fields in the Lagrangian. These two, AI and psi are the 2 fields that appear in the chiral multiplets. And these 2 are the fields that appear in the vector multiplets, the vector fields and their fermionic friends. And so, and the Lagrangian is like this. If supersymmetry is exact, the Lagrangian is like this. You have the usual kinetic terms for all these fields, and the usual gauge interactions for all these fields that are determined by the gauge principle, as you saw this morning. And then on top of these usual gauge interactions, you have additional interactions that are determined by the superpotential and by the gauge structure of the theory. So you have 2 types of new interactions. These are Yukawa interactions that involve 2 fermion fields and a scalar. And there is also a scalar potential which only involves scalars. So let's see how the I'm done. 10 minutes. Let's see how the Yukawa interactions are made. So you have 2 types of Yukawa interactions. One type of Yukawa interactions involves twice the fermion fields that are the partners of the scalars, and possibly 1 scalar. Okay. This is just the double derivative of this function with respect to AI and AJ. Okay. And then there is another type of Yukawa interaction, which instead of involving twice this type of fermions, it involves, it combines the fermion, which is the partner of the scalar in the chiral multiplet, and the fermion, which is the partner of the vector in the vector multiplet. This Yukawa interaction, which only involves these fermions, is determined by the superpotential. This Yukawa interaction, which involves the partners of the gauge bosons, that are also called the gauginos, and one of these fermions, are determined by the gauge structure of the theory. This is the gauge coupling associated to the gaugino A, and this is the generator, the symmetry generator associated to the gaugino A, if you want. Okay. So, for example, in QCD, this T would be the Gelman matrices. In a SU2 gauge theory, if this transform under the fundamental, this would be the Pauli matrices. So anyway, what's important is that this interaction is determined by the gauge structure of the theory, and this interaction is determined by the superpotential. And then there is the scalar potential, which is a function of only the scalar fields in the theory. And the scalar potential also has 2 pieces corresponding to these 2 pieces. These F and D are defined by this formula. They are just functions of the scalar fields of the theory. And so there is a piece which is just the absolute value squared of these F objects. So this part is again determined by the superpotential. You just derive the superpotential once with respect to the scalar fields, and then you compute the square. And this piece, as this one, is determined by the gauge structure of the theory, because you see that this function of the scalar fields is again determined by the gauge fields and the gauge symmetry generators. So anyway, I don't want you to remember the exact structure of this Lagrangian. I just want you to remember that the structure of this Lagrangian is determined first by the gauge structure of the theory, so what is the gauge group and what are the quantum numbers of the fields under the gauge group, and second by the superpotential value. And there are Yukawa interactions and the scalar potential. As always, when you have a theory, you can wonder what are the symmetries of this theory. In the case of supersymmetry, there are two types of possible symmetries that you can consider.